We will look very briefly at the theoretical background of Osmoramism before we look at the practical side of things. So in general, the idea of Osmoramism is that we decouple the physical SIM card from the location where the SIM card is used. So on the one hand side, you have a modem or a phone or something like that. No, sorry, it's actually on this side, the phone or the modem on the right-hand side here. And normally, where you have your phone or your modem, you also have the SIM card. There's just a couple of traces in between, and they're physically co-located, and you cannot normally locate them remotely. And we basically forward this through a relatively complex system, which I will explain in a bit. And on the other hand side, we have smart card readers. In this example here, using a Osmoramism, which is an 8-slot smart card reader, but you can really use any smart card reader that you can find on the market. So as long as it's supported by PCSD and PCSD Lite, more precisely, which is the standard framework for smart card readers on Linux and Mac OS as well. So we have smart card readers somewhere here, we have the modem somewhere there, and we have some hardware in front of the modem, which we built around the SIM trace device. There's a special firmware called CardEM for card emulation, which picks up these signals and emulates the physical interface of the smart card to the modem. And it attaches over USB to a Linux machine where then software called remsim client is running. And this software then communicates over network with other components of the Osmo-remsim system. So we have some hardware next to the modem or phone. There's multiple hardware projects out there that support this, and we have some hardware that has SIM card slots where SIM slots are inserted. And then we have some open source software projects of the Osmoramism project in between. The arrows here between those software components symbolize the TCP connections that are established between those. There is a custom protocol called RS Pro, that's the remote SIM protocol, which we run over some additional layer and then TCP. And basically, the remsim server is a central component in the network to which all the other elements connect. And the other elements is the remsim client, which is the part that's located next to the modem, and the so-called remsim bank daemon for SimBank, which manages one or multiple SIM card readers, and that also connects to the remsim server. And the server then associates slots on the SIM card side, on the bank daemon side, with slots on the modem side. And you can set up mappings, so-called mappings, between a given reader slot over on the left-hand side and a given modem on the right-hand side. And those mappings can, of course, change dynamically over time, which is useful for setups where, let's say, you have more SIM cards than modems. So let's say you want to test something with lots of different SIM cards at one location, for example, roaming testing, where you have, let's say, one modem in Germany and one in France and one in the UK and so on. And then you have SIM cards from dozens to hundreds of operators, and you want to do a test, then you can say, well, before I run the test, I provision this SIM card to that modem, and then I can test, let's say, with a T-Mobile Germany SIM in the UK or some constellation of such kind. And once the test is done after 5 minutes, you can do the same with another SIM card or what so on. And that brings us to the use cases. So one, for example, is roaming testing, where traditionally people are sending SIM cards in mail or postal packages around the planet, and everyone has to have all the SIM cards locally. And with the system, you can dynamically provision remote SIM cards at the other end of the planet to a modem somewhere completely else. There's other testing in cellular network where it's used, such as voice quality testing, which is a similar situation. You want to test with different SIM cards from different operators in roaming and non-roaming scenarios, and then you set up a voice call and do some measurements on the voice quality. And other use cases, just giving some examples. Fundamentally, there's nothing in Osmoramism that's tied to the SIM card itself. So it would also work with other smart cards as long as they use this ISO 7816 standard with the T0 transmission protocol. So you could use the same to forward, let's say, a bank card or some cryptographic smart card or anything like that. It's just that the SIM use case was the primary use case to which it was developed, but fundamentally it works for anything in other smart cards. Although a number of other smart card applications use a different protocol called T=1. So if somebody needs that, it would have to be added to the software components to support this. That's currently not supported. Okay, before we go into a practical demo of how this looks like, I open the round for questions at this point to make sure the theoretical background is clear. Yeah. Max states any plans for eSIM support. I'm not quite sure how. I mean, maybe you can explain how you see that, because an eSIM is a complete. It's a virtual profile. So, are you foreseeing like a physical interface to EU ICCs, or how exactly do you?
Pretty much. For example, we have hardware fixture like the modem, which is used for a bunch of tests, and we try SIM version this, SIM version that, and so on. And now we want to try eSIM, but it's old hardware which just does not support it. So if we can present this eSIM through remsim as just yet another version of the SIM which device talks to, then it should be rather easy for us.
Yeah, I mean, there's nothing that prevents such a usage pattern. The way how you would do this is basically you would put an EU ICC, which is the physical chip that hosts the SIM card or the eSIM profiles. You would put an EU ICC in a smart card reader, basically over here. I mean, in the lab or as a hack, this can be done. We have a solder type adapter. Let me just quickly. You wanted to look at the web shop anyway. There is this device here where you can solder an MFF2, that's an EU ICC chip on it, and then you have this flex cable interface where you can plug one of these cables, and that then goes into a smart card reader, and then you can of course fully access whatever eSIM profile is currently installed on that EU ICC. If you want to switch to another eSIM profile, you would need the so-called LPA, the local profile. I don't know what LPA expands. So that's the bit of software that runs normally in a smartphone that talks on the one hand side to the SMTP, which is the eSIM backend of the GSMA, and on the other hand side, it talks to the SIM card. So someone would need to implement an LPA, which then talks to this EU ICC and to the backend in order to switch the profiles. But yeah, and then as a second step, of course, this is a bit of a clumsy hack with the flex cable and so on, but there's of course no reason why one couldn't build a smart card reader directly where the chip can be soldered to. I've also seen some vendors that offer EU ICCs in the normal plastic SIM 2FF form factor. That would, of course, be useful in this situation. Yeah, you cannot do without the physical EU ICC, because the EU ICC contains a certificate that is issued by a certificate authority that goes back to the GSMA. And you can basically only deploy or install an eSIM profile into an EU ICC that has a proper signed certificate installed. if that was not the case, you could, of course, in theory, do that completely virtualized, but that's exactly the point, that they don't want to do this. They want a secure UICC, and the encrypted eSIM profile is installed to that, and the key materials are all not accessible to you. Okay. Yeah, in case there's other questions or more background information required, there's a user manual. So from the Osmoramism project page, there is a link to the user manual that gives a bit more theoretical background. And there's also an entirely theoretical presentation, an older presentation, a recording, video recording here, in case any of you is interested in that. Okay. No other questions at this point, I presume. Okay, then I'll proceed with the quick demo. So the setup I've put together is basically, we have on this side, we have not a phone and a SIM trace device, but we have a Sysmo QMod board, which is looks a bit like this. It's a circuit board where you can plug 4 mini PCIe modems, and all of those, and the board itself contains the SIM trace hardware, the card emulation firmware to pick up the SIM signals, so we don't need to work with these FPC cables and so on. That's what I have in my setup here on the modem side. And attached to that, well, actually, I can maybe quickly rotate the camera to show you. So there is that's basically the setup we have here. Is a quad modem board that has one modem installed. This is connected over USB cable here to this Raspberry Pi 3. Which then has a Ethernet connection basically back to the network. That's the modem side, and for the SIM card side, I'm actually using it plugged into my laptop one of these very small Gemalto readers that has a SIM card inside. It's a normal commercial SIM card for a T-Mobile Germany, so there's nothing special about that. It's just inside that reader attached. So there's a question from Sec. I'm wondering why there's a connection between the remsim client and the remsim bank key. This is done in a way that the actual traffic goes directly. It's a bit like SIP and SDP, or SIP and RTP, if you want to look at VoIP as a comparison. So the control plane, the setup, the configuration happens via the server, but the communication of the actual TPDUs, that's the traffic between modem and card, that is handled directly between client and bank daemon. That's mostly done because maybe there's a high latency. Some people want to operate this over VSAT backhaul or satellite. And that, for example, then this maybe can be avoided depending on the network topology. Also, the server, for example, it could completely die while all the existing mappings continue to operate. So you can even restart, for example, the remsim server, and the communication here is not interrupted. There's a question from Konstantin. Kostiantin. I'm sorry, bad reading about whether there's an APDU trace info shared. I think this is implemented. I would have to check again the code. I think it's possible to generate GSM tab output just like the tracer. You will see in a second, you see it in the log files, but I think there's also an option to generate GSM tab traces. We can have a look at that. We can even try to demo it in a couple of seconds. Texas, yeah, old-fashioned. Well, you know, everything in Osmocom is old-fashioned, of course. Yeah, so yeah, let me just quickly switch over to a couple of shells that we have here. So on this window on the right-hand side, we have the bank daemon log output. That's already from my testing before the talk, which we see here in the backtrace. Here we have the output of the REMSIM client. I increased the font size so something is readable, but then of course everything wraps, so it becomes less readable. And here we have a shell to use the so-called REMSIM API tool, which we use to configure the server. And we have the modem AT command interface here, so we can check what kind of modem it is and talk to the modem. And here we have the REMSIM server log output. Now, all of these components are already started. In this particular setup, I'm running the REMSIM server on the same device as the REMSIM client, but there is no reason to do so. You can run all of these three components on different IP addresses on different machines. They all talk only TCP to each other. There is this REMSIM API tool, which we can use to inquire the server. You need to specify the IP address of the server, and it's just a small Python tool to send some REST requests to the REST API of the REMSIM server. And if you don't provide any further arguments, it tells you the status, what is connected. So what kind of clients do we have connected? We have one client connected at the moment. And it has the software version of the client, and it says the ID 00. So all the elements in the REMSIM system have numeric identifiers. So we have on the one hand side client identifiers. So this is C0 is client 0. And we have a 0 behind the colon, which means slot number 0 at client 0, because every client could have multiple slots. Likewise, here we have bank daemons or banks connected. We have one bank connected, which is B1. So that's the bank number 1. And bank number 1 has, he's also again printed bank ID. And it has 8 slots in this configuration. So we have 8 different slots. At least that's what the software reports, because it's told so. And we have the list of slot maps, which is empty at this point. So we do not have any mappings configured between the server and the client at this point. We could, of course, also use --help to see more about it. So we can also only see a subset. So if we only want to see the clients or only want to see the bank daemon, that's fairly trivial to get that output. Now, if we look at the modem, for example, if I do 80 plus CSIM, it will tell me error, because right now there is no SIM card is mapped, so it cannot read from the SIM card. I think ATCME still. Well, I thought I would get a more verbose error if I set those parameters, but anyway, I mean, we have an error. If we want to talk to the, 80 plus CIMI is what I wanted to do, not CSIM. But anyway, we cannot read the IMSI of the card. Anything we try to do regarding the card fails because there is no SIM card connected to it right now. Now, if I add a mapping to the bank, this works with the -m command here. That's basically here, or maybe the more easy to remember, the -- create slot map. Let's do it like that. And then we say bank ID 1, slot number 0 at bank ID 1, client ID 0, client slot 0. And once we do this, we will see a lot of activity in the other windows. So I have an extra B here that doesn't work in the command line. So now it's created, and we see already there's some activity here. We see the ATR has been received. We see some APDUs already here going basically in the log. That's what the modem is doing. Also here on the AT command interface of the modem, we see the modem is reporting status as it goes through the reading of a phone book and so on. And now if I do the 80 plus CIMI again, it actually could read the IMSI of the modem at this point, because now there is a connection established to this SIM card on the reader. And then we can look a bit more at the logs. So here at the, this is the bank daemon. We see an APDU trace of whatever is happening. We see lots of activity here because, of course, the entire SIM card is dumped at startup by the modem. Now, once it's running, we only see a few small short APDUs. I think it's only for the proactive SIM, basically the regular polling if the SIM card has some new stuff to tell the modem. But apparently it doesn't, because we only see very short strings here. Likewise here on the server side, well, we don't see all that much activity. It's just some state changes of finite state machines. So we see there's a new slot map that is created. Not sure why it's logged twice. Maybe that was the failed attempt, the first one, not sure. But then we see, well, it is some event push to push the configuration. So the configuration is pushed to the server and to the bank daemon. And that's all that the server is doing. And as you can see, that even though there's traffic with the TPDUs, they don't go through the server, but they directly go to the bank daemon at the other side. Oh, sorry, the bank daemon is here to the client at the other side. Let's look at the client versus the bank daemon. If we look at those here, add a couple of empty lines and wait for the next TPDU. In a second. Well, now it takes longer than the demo effect until the modem is doing the next. Yeah, now we see. So here we see the APDU, and here we see also basically some message dump and debug logging of the client side. And if I were to delete the mapping again now, that's delete slot map, then it's removed. We see some state changes here. Well, the modem probably, no, actually, it already hangs at this point. I was about to say, well, probably it has the information cached, but no, we see some timeouts are happening at this point because the modem suddenly can no longer access the SIM card. The connection has been removed between those two. And it will, at some point, it will time out and give us an error. Yeah, I mean, that's already it. Is there any security? Yes, well, no, there is no security. And yes, you can connect to any of the map sims by guessing the host and ports. It's not supposed to be operated on a public internet or an unsecure network. The normal deployment is to do this over a VPN of some sort, which takes care of transport security between the different elements. Of course, if somebody wanted, they could add TLS support or something to those TCP connections. There's nothing fundamentally against that. It's just not implemented because, yeah, the existing users, they have VPNs anyway in those setups, so it was not required. Yeah, so that was really already it. I mean, we can still look a bit at the config files maybe, which should be interesting. So let's just open another terminal window. On this device, that's the Raspberry Pi. The GSM tab. Yeah, thanks. We will look at that quickly. Thanks, Kevin, for the reminder. So here we have the Raspberry Pi that I was showing with the camera, which runs the REMSIM server and the REMSIM client. So we see the REMSIM server is executed without any command line arguments. There's also no configuration for the server itself. It's completely volatile. So once the server is restarted, there is no persistent state. You would have to, whatever management backend you have, whatever application on top, would have to recreate slot maps after the server has restarted. so there's no configuration, and it just listens for incoming connections from clients, from bank daemons, and via this REST API. And on the other hand, we have this remsim client ST2. There's several different clients implemented. ST2 is for the SimTrace2 family of devices, which is basically, well, the SimTrace2 itself, the actual SimTrace hardware. This is OsmoQmod, which I just showed in the camera. There's also another board that is not publicly available. It's a customer-specific board and so-called OWHW. And now we have a new board which is coming up. It's in the prototype phase already working, which is an NGFF breakout board with integrated SimTrace card emulation capability. So a bit like the NGFF card EM device that's already out there and open source hardware. And also this new board is also open source hardware, which has basically a SimTrace and an NGFF card EM on one board. So this family of devices is supported by the remsim client ST2. There are some other clients. One is basically just a command line shell for doing APDUs. It's for debugging. And the other implementation is, I think, rather interesting. It's a PCSC IFD handler. So that means you can basically have a virtual remote smart card reader on your Linux system by this. So instead of attaching to a modem with physical hardware, you can basically represent the remote SIM card as a local PCSC reader to any PCSC application on the PC. So that's a couple of different flavors. So let's look at this, the command line. The -I is the IP address of the server to connect to, and the remainder of the parameters here are basically the USB parameters. If we do SimTrace2 list, we see the different SimTrace devices here on this system. As I said, it's a OsmoQmod in this case, which has 4 modems, and we have for each of those modems a different USB interface. And these parameters, vendor ID, product ID, USB configuration interface, and the path to the USB device, because of course we have multiple devices with the same vendor and product ID here. So we need to specify the path to uniquely identify them. And then finally, the Z0, N0 is basically client ID 0 and slot number 0 of this client. That's all there is to the execution. We have some systemd as part of the Debian packages. We have some systemd integration, which splits this configuration in Osmocom. It's the default osmo-remsim client. So here we have the global parameters that are the same for all of the remsim clients that we start, and then we have the configuration parameters for each of the clients that we may be running on the system. And then if we do systemctl status grep remsim client, we will see this is basically done via a systemd service that can run multiple instances. So the @0 is the first, the slot number 0, and so on. We can start more of them as needed on the device. So that's it in terms of this configuration on the client side. Now let's have a look at the configuration at the server side. So here we have one process running. Don't be surprised by this very large memory usage. That's because I'm using address sanitizer in this build. It's my R&D machine. So that is an artifact of that. Of course, we don't need that much memory. So yeah, we run the Osmoramism bank daemon again with the -I and the IP address of the server to connect to. And there's a configuration file. The CSV file that is used. And that basically says for bank ID 1, slot number 0 at that bank ID, use the PCSC device with this regular expression to map to that. So if I do PCSC scan here, I see I have two readers, 0 and 1 here. Well, it's not so readable, but basically the PCSC reader names are what is listed in the CSV file, so you can map the PCSC reader to a certain bank ID and bank slot. And that's really all there is in terms of configuration. Now the question, well, maybe if there's questions about configuration, maybe bring them up. Meanwhile, I look at the GSM tab. Let me just quickly see. Yep, we do have GSM tab in the remsim client. And we can also see that it's hard-coded to localhost, at least here. Yeah, it's not configurable yet. Patches are welcome, so it's only sent to localhost. But what I can do now, I can SSH again to the machine where the client is running. I do a TCP dump minus npi any S0W TCP port 4729, no UDP. No PCP dump. That's quick to fix, usually. Okay. Meanwhile, stable has changed to old stable, so I guess I need to update some sources here. No, it's Buster. No, it should be somewhere here. It says Buster. So why does it? Does anyone know why it cannot? IP address not found. So Raspbian Raspberry Pi org doesn't resolve anymore. So in general, it works. That IP address also works. Why can it not fetch that? Not found. Why does it not find that anymore? If anyone has useful advice, CP dump. It's step 10U2, but why does it not update that? Yeah, this must be accepted explicitly. The apt secure man page. Yeah, but how can I explicitly accept it? Does anyone know off their head? Otherwise, I hope I can just. Okay, that should do the trick. So let's add verbose into the mix. Okay, so now we have TCP dump running for the GSM tab packets that we expect to be originated. So now what we will do is we will again install the slot map, which should give us some nice traffic over here. Yeah, and TCP dump still says got 0. So doesn't work as expected. Okay, let me quickly check the source again. As you can see, it's not something that is used a lot. Is tracing enabled by default? Well, yeah, that's a good question. We have GSM tab host. Yeah, it well, actually it is set. Okay, yeah, it's not implemented apparently. You know, it's the variable is declared in the struct and it's set, but nobody's using it. So okay, no, there's no GSM tab support yet here. We can confirm that. So we could quickly add that to the code maybe later. So no, it's not supported yet. What exists though is there is a on the osmocom org is a Wireshark fork. If I could type, it would actually show. So there is a Wireshark version, LaForge RS Pro, that contains a dissector for the protocol spoken between the SymTrace elements, and then of course the APDUs are in there as well. So that would be an alternative. But I don't think I have a version built with this protocol readily compiled now to show you.